Alright, so in this video I got my 1000-volt battery pack, my multimeter, which is reading 2 milliamps of current from the 1000-volt battery pack right directly to the motor coils, and I'm measuring the amount of torque, and I'm holding it right against the wall so there's no fluctuations, or trying not to. So let's just say a low of 1.15 newton meters of torque, and we're only pulling 2 milliamps. And I will move this just very little bit just to show you that we are consuming and we are pulling right on the coils. So at this power level, we get that much newton meter, 1.17 now, of newton meters of torque on this motor. On the 6 high resistance coils of 480 kilo ohms worth, all in series, of 41 gauge wire. And we only have 2 watts of input. It's technically less because the voltage goes down when I put a load to this. But I'm gonna let this rest against the wall. It shows more because it's on an angle. But now I will show you the proof that, at that voltage, nope, not that. Nope, not that. This. So, let's say 1000 volts, and we had 2 milliamps of current. It's exactly 2 milliamps at that. That's 2 watts exactly of power consumption to the coils. That's how much power is going into this motor. 2 watts of power. Now, if I go to the conversion, I counted 21 RPM, and I didn't get this value. I have a better value now. You saw it was 16, 17, but I'll put it at 16. So we have, and this is in watts, we have a 2.55 watt output versus a 2 watt input. And I'm literally measuring the amount of torque coming off of this now. It's actually a little higher now. But this is just to show that there is a higher output than input. I've got complete proof here now. Other than the fact that the RPM could vary slightly, but I did count it at 21 RPM. And I will take this off. I don't need this anymore anyway. So that is the RPM, and I counted that RPM by having my clock on my phone, and I just used this every time it hit by, and every time it hit by I would count it, and then it came up to 21 RPM, so 21 revolutions per minute. So that's how I got this. And I could sit here and do this for 1 minute and prove it. That is 21 RPM. But I don't think I need to do that. I'm sure you guys believe me. But yep, that's 21 RPM at 1000 volts of 2 amps or 2 milliamps of input. And it won't measure now because it's such a low amount, because it's pulsing now. So the only thing that I think that could be giving us a higher output power is because the output is pulsed current. So I don't know if you can count the pulses towards the RPM. I mean, yes, that is the RPM, but it's not a full amount the entire time, like it's pulsed. So I don't know if I'd have to divide it by 6, because it's pulsing 6 times throughout one revolution, or does that not matter? But I have a higher output than input on power conversion from torque to speed, RPM, from input in watts. And I have proof right here. This is proof. So, and I knew the torque on this felt a lot, and I know you guys can't like feel that, obviously, because you're not here. You can't tell how much power is actually being delivered to this motor on how little bit of power. But yeah, now I was able to show you guys power in, power out. And yeah, there's a lot of torque actually. I mean, it takes a lot of force to push that back in there. Like it's not easy. Like, if you look at my hand, that's not an easy amount to move. I mean, yeah, I got proof. This is yeah, I think this is over Unity, right? Now to convert it back into electrical energy is another thing. So I only have a half a watt, or 55.55 watts to work with, and then you have the inefficiencies of generating that electricity, and then the inefficiencies of converting it either back down to a low voltage or directly to a high voltage. So either way, there's going to be another efficiency loss for generating. So we have the power consumption, we're saving on that, but now the generation side is another whole ball game. But yeah, either way, I have proof that my motor produces more power output than input.